that integration and we found out for equation for N0 and P0, but these expressions are now in terms of NC or NV and in terms of EF, because we need to find out where the Fermi level would be, and with respect to the valence or the conduction band. So we have got both the expressions for N0 and N0 and P0. But then we have got two constants, NC and NV, and the DOS functions depends on that. And we know that NC and NV are constant, provided that the material is same and we are keeping at a fixed temperature. So with this we can find out the value of NC and NV for some ratio of the effective masses for electrons and the holes. Okay. So the point here is that when we talk about this equilibrium concentration of any of the carrier, these depends on what are these effective DOS constant. Okay, so if temperature changes, this NCNV is going to change, and it is going to, as I've said, it also depends on the Fermi energy level, where the EF lies. So later we will see that when we dope the semiconductor, we can this EF will be shifting. The distance between the EF EC or EF EV will be different. Okay. So now we know that intrinsic carrier concentration Ni should be equal to Pi, and intrinsic Fermi energy. So at the point when we have established the equilibrium between these two carriers, the intrinsic energy level has to be equal to the Fermi energy level. Okay, and we have also said that it would be qualitatively in between the two, and to retain the symmetry, it should be exactly in between. So we have this N0 expression. So we have already found this N0 expression, and we have got P0 equation, but we know that NiPi should be equal, and these are intrinsic, so we can equate them. So we can equate Pi equal to Ni, and then if we multiply this on left hand side and right hand side, this is what we are going to get. And you can understand that we are trying to find out some expression for Ni. So obviously this NC and NV are the constants, and then if we these two terms, if we adjust them, what we are going to get is EC minus EV. And with this, what you can replace, EC minus EV is nothing but the band gap of the given material. So please note down these equations. Whatever equations in the red, please note it down, because so many equations are going to come in these slides, and we are going to find out some relation between here and there. Okay, and we are also going to find out what is the physical significance of it. So let us say from this particular expression, what you can see is NC, NV are already constant for a constant particular temperature, right, for a material. And we know that band gap is also constant for a particular material. For example, silicon 1.11 or 1.12, right? So the point here is that when we talk about the intrinsic carrier concentration, it is always a constant provided at a constant temperature. So Ni is constant, and another part is it depends on the band gap and not on the Fermi energy level. So it is independent of the Fermi energy level. So what does it mean? So even if we dope any semiconductor, later we will see that the Fermi level is going to shift either towards EC or towards EV to balance the equations. Okay, but it doesn't alter the value of Ni. So let us try to find out some Ni values at t equal to 300. Now here the Ni value will be, there will be some discrepancy between the theoretical and the practical values, and it is happening because the Ni depends on NC and NV, which depends on the mass of the carriers, right? So these effective mass basically are dependent on temperature. Normally we neglect it for basic calculations. Okay, so this dependency is going to creep in. So if you try to plot this, you can see that x-axis is a temperature dependent. So Ni goes on decreasing as you are changing the as you are increasing the temperature, and for Si the Ni is higher compared to gallium arsenide. Another discrepancy arises because of the approximation values, and that difference could be around up to 2. So these are the actual values if we can calculate at 300. So you can see this value of silicon, that is what you have to remember, that we will be using 1.5 into 10 raised to 10. Already we have used probably in one or two examples. This is NC, this should be NV, and then this is NI. So NC, NV you can calculate whenever you want. So now let us talk about the EFI a bit more. So we have already argued qualitatively that the Fermi level has to be near the center or in the uh, some mathematical manipulations using the natural log, and we get this particular expression. Now what do you know? This is EC plus EV, and this one is second term is KT ln of NV by NC. Now we know that expression for NC and NV, and again here temperature term is involved, and Mn and MP. So these are the effective masses are involved. So obviously a material will be at the same temperature, right? So this thing will go, and what this term will remain will be in only in terms of the masses only. So half EC plus EV is the first term, and this 3 by 4 KT ln of MP by Mn star, of course both are effective masses, that is the second term. Now, as in the previous slide, I have discussed that actually these masses are different. For electrons and for holes, the masses are different, and they depend on the temperature as well. Okay, so the point here is that suppose for simplification, if we assume that the mass of electron and mass of holes are more or same, what is going to happen is this second term will vanish, and what we will get is EFI is just EC plus EV by 2. Okay, so if with the assumption, which is okay to assume, if the carrier masses are equal, then the Fermi level will lie in between the two bands, conduction and valence band, and that's why EFI, EF and E mid gap will be the same whenever we talk about the intrinsic level of the Fermi level. But however, so this was our assumption. These two masses are equal, but obviously these two can be, these are actually different depending upon the temperatures, and actually also it is different. So what happens is MP, if it is greater than Mn, obviously now what will happen? This EFI minus E mid gap, that is what we want. So which will be controlled, or what you say, manipulated by the second term over here. So if MP is larger than Mn, obviously the the EFI will be towards the conduction band, that is above the center of the band gap. So center of the band gap is kind of a fictitious reference for us. Okay, and if Mn is greater than MP, obviously it will be lower than that. So the point here is that the DOS function is related to the effective mass of the carriers, and larger the effective mass means the larger will be the DOS function. So that is what the physical significance is, what we can use later for when we see the effect of the doping. So in other sense, when I say doping, it means we are adding some electrons or holes, right? So the point is, when we add the impurities to the extrinsic semiconductor, we make it, when we add the impurities to intrinsic semiconductor, we make it extrinsic, right? We make it impure. So obviously this EFI, or the intrinsic Fermi level, has to shift. Okay, and these shifting depending on what kind of doping I add, whether I'm increasing the number of electrons or holes. Now, why this shift has to be? So that this semiconductor maintains one balance between the number of electrons and holes, and ultimately this Fermi level is adjusted accordingly. So with this basics of understanding of this EFI and EF, let us start now talking about the how the extrinsic semiconductor will behave to that. Okay. So Fermi level is related to distribution function. So we can have this Fermi level, and then we can have our own. Sorry, I think my animation is messed up. The point is, so you can see here, this red one is EFI, and then depending upon what kind of what you say doping I am doing, this EF has to move. So if EF is greater than EFI, the electron concentration is higher, or if I'm doping with the what I say pentavalent, then obviously the electron concentration would be higher, and obviously the vice versa is true, that when the whole concentration is increased, the new EF will be shifting towards the valence band. Okay, so you can find out when EF is greater than EFI, the area of electron concentration will be higher, and the area of hole concentration will be lower. So the exactly opposite will happen when EF is lesser than EFI, and you will have EF, which is towards the valence band, as I've told, and you can see the area is higher as compared to area of hole concentration is higher compared to the electron concentration. So let us now think of some other forms of the equations which gives us the concentration, so that we can interpret the things in a different and better way. So we already know the expressions for this N0. So what you can do is you can add this term EFI to these two terms EC and EF. Okay, so now what is this EC and EC and EFI? So you want to separate these terms. Okay, so you can see two exponential terms are here, and we have one EC minus EFI and one is EF minus EFI. So here, if we can substitute this particular term EC minus EFI, that is, we know that it is the intrinsic concentration, and this one is already the thermal equilibrium. So what you get is, we can now write N0, which is in terms of Ni. However, this bracketed term what we have is now telling us what is the difference between the EF and EFI. So if from this expression, what I know, if I know the intrinsic carrier concentration, let us say temperature is 300 degrees Celsius, so Ni is constant, temperature is constant. So in that case, and if I know the N0, what I can determine is the Fermi level in that semiconductor with respect to the intrinsic level concentration, and also I can find out the value of P0, which is equal to N0. So this expression would be useful to determine the relative differences between the Fermi level and the intrinsic Fermi level. Already we have talked about N0, product of N0 P0. We know that it should be equal to Ni square. We haven't proved it, but now we have the expressions which we can use and we can prove it. So now when EF is greater than EFI, definitely electrons are higher, and the vice versa is true for P type. So respectively for N and P type semiconductor. Now as we want N0 P0 product, we already have the expressions for N0 P0. Substitute them, and then after the rearrangement, what you get is N0 P0 is now what you say NC NV exponential of this. And that is nothing but the Ni square, which we have found out in the previous slides. Okay, so here we can prove it very easily, that the intrinsic concentration should be equal to the product of the two carrier concentrations. So what's the time right now? It's 5:40 only. Okay, so today we will stop because tomorrow, I mean, whatever the next lecture will be the last lecture on this. So what you can do is you go through whatever we have done today. You please make a list of what you call whatever the important expressions that we have, and that list we will use in the next class. So that we can solve some numericals over here. Degenerate semiconductor is a small part which we will learn next time, and probably we will have we will solve some numericals. Okay, so it may happen that the next class can be a bit what you say prolonged. Okay, so be ready for that. So right now I'm giving you almost what more than 20 minutes. Okay, so next class we will adjust it so that there will be a link when we are solving the numericals, and it may take a bit longer. Is that fine?
Yes, sir.
Yeah, okay.
Sir,
Huh.
could you provide the GIFs that were used in the previous slides?
GIF? Which GIF you are talking about?
The purification and those processes, because those, like, it's not like we cannot visualize those things.
Acha, acha, because now it is PDF, right?
Yes, sir.
Yeah, okay. So yeah, I will try. I will send it. Okay, I will send those GIFs. Fine, no issue. Okay. Anything else?
Sir, and today's slides also.
Of course, I will give the slides definitely, because I'm asking you to review it, right? So immediately after this lecture, I will be giving you the slides. Okay. Anyway, but
Okay.
tomorrow next lecture will be prolonged. Okay, it will be extended. Okay. Okay. So thank you. Good night.